Module 7, Foundation Fieldbus. When control moves into the field, this module marks a philosophical break from everything before it. Up to now, even with Fieldbus, there was still an unspoken assumption. Open quote, real control lives in the controller. Close quote. Foundation Fieldbus challenges that assumption directly. It doesn't just change how devices communicate, it changes where control actually happens. And that's why it's one of the most misunderstood and most ambitious industrial networking concepts ever introduced. Foundation Fieldbus, the core concept, not the marketing version. Let's strip it down to first principles. Foundation Fieldbus was designed to interconnect instruments, actuators, and controllers using a shared digital bus with standardized behavior across manufacturers' EL leap. The real leap is this. Open quote. Control logic no longer has to live in a PLC or DCS. Close quote. It can live inside the field devices themselves. That single idea changes everything. From centralized control to distributed intelligence. In traditional DCS PLC systems, sensors measure, controllers decide, actuators act. The field devices are mostly obedient messengers. Foundation Fieldbus flips this model. Field devices become intelligent, executable, cooperative. Transmitters can host function blocks. Valves can host function blocks. P loops can execute in the field. The tutorial states this clearly. By using function blocks, Foundation Fieldbus attempts to move control right down to the field level, eliminating the need for a central controller for many functions. That's not in-creme architectural rebellion. Interoperability, the promise that made it revolutionary. Now let's talk about the promise that sold Foundation Fieldbus to the industry. Interoperability. The idea was bold. Devices from different manufacturers plugged into the same network, behaving predictably, executing standardized function blocks. The tutorial illustrates this visually. Multiple vendor-specific systems replaced by a single common Fieldbus system. In theory, a flow transmitter from VE from vendor B, an operator interface from vendor C, could all work together without custom glue. That was unheard of at the time. The operator interface from controller to window. This is one of the most subtle but important shifts. In Foundation Fieldbus, the operator interface is no longer the brain. It becomes a window into distributed control logic, function blocks executing in the field, process values and diagnostics flowing across the bus. The tutorial makes this explicit. The operator interface displays data and transfers high-level control information, like set points, but does not necessarily execute the control itself. This means losing the HMI doesn't kill the control loop, doesn't necessarily stop the process. Control becomes physically closer to the process. That proximity matters for stability, latency, and resilience. Why this idea was so attractive to process industry's Foundation. Fieldbus aligned perfectly with process plant realities, slow changing processes, high emphasis on diagnostics, long cable runs, hazardous areas, need for intrinsic safety, desire to reduce cabinets and controllers. By embedding intelligence into instruments, wiring reduces, cabinets shrink, diagnostics explode in a good way. And because function blocks are standardized, engineers can reason about behavior, not vendor quirks. The reality check without killing the vision. Now let me be honest, in an engineering way. Foundation Fieldbus did not fail because the idea was wrong. It struggled because the idea was ahead of its operational maturity. Distributed control introduces complex commissioning, scheduling dependencies, new failure modes, higher skill requirements. But none of that invalidates the core concept. It simply means, open quote, this is a powerful tool, not a universal one. Close quote. The mental model to lock in Foundation Fieldbus is not another protocol. It is a control philosophy. Intelligence belongs near the process. Devices should cooperate, not just report. Operators observe and guide, not micromanage. Vendors should interoperate at the behavior level. Once you see it that way, Foundation Fieldbus stops being mysterious. It becomes a logical, even inevitable, response to centralized control limits. And now that you understand the concept and the promise, the next step is unavoidable. How does this actually work? Electrically, logically, and deterministically on a shared bus. That's where structure, layers, and function blocks come into play. Foundation Fieldbus architecture versus OSI, why the user layer had to exist. This episode is where Foundation Fieldbus reveals its true ambition. Up to now, OSI has been our mental reference frame. Layers for signals, frames, routing, transport, applications. Clean, logical, contained. But Foundation Fieldbus looked at OSI and said something radical. Open quote, OSI is enough to move data, but not enough to make devices behave the same. Close quote. That realization is exactly why Foundation Fieldbus adds something OSI never had, a user layer. Why the classic OSI model wasn't enough for process control. OSI was designed to solve a communication problem. How do heterogeneous systems exchange data reliably? It was not designed to solve a control problem. How do heterogeneous devices execute identical behavior? OSI can guarantee bits arrive, frames are intact, messages are routed. OSI cannot guarantee a valve from vendor A behaves like a valve from vendor B. A PID block executes with the same semantics everywhere. Control logic is portable across manufacturers. For office networks, that's fine. For process plants, it's unacceptable. Foundation Fieldbus architecture, a deliberate simplification. Foundation Fieldbus deliberately simplifies the OSI stack. Instead of 7 layers, it uses physical layer, data link layer, application layer. Exactly as described in the tutorial, use something important. Foundation Fieldbus values determinism and clarity over architectural completeness. Layers that don't directly serve process control are collapsed or eliminated. But then comes the crucial addition. The user layer, where interoperability actually lives. Above the application layer, Foundation Fieldbus introduces the user layer. This is not a networking layer. This is a behavior layer. The user layer defines standardized function blocks, their inputs and outputs, their execution rules, their scheduling expectations, their interaction semantics. This is the missing SED. OSI says, open quote, here's how data moves, close quote. The user layer says, open quote, here's what the data means in control terms, close quote. Hashtag function blocks, the currency of interoperability. In Foundation Fieldbus, devices don't just exchange values, they exchange function blocks. Analog input, AI, analog output, AO, PID, ratio, arithmetic blocks. These blocks are standardized. A PID block is not vendor A's PID, vendor B's PID. It is the PID block with defined behavior and parameters. This is what allows a transmitter from one vendor, a valve from another, a controller or interface from a third mine, to participate in the same control strategy. The tutorial makes this explicit. Function blocks built into field devices allow control to execute at the field level, eliminating the need for a central controller. That interoperability cannot be at one. Why the user layer had to sit above the network. Notice something subtle. The user layer does not care about cable type, token passing, frame timing. It assumes, open quote, communication already works, close quote. What it defines is behavioral consistency. This separation is intentional. Network layers move data, user layer defines control logic meaning. That's why Foundation Fieldbus could promise multi-vendor interchangeability, portable control strategies, vendor-neutral behavior. Not at the wire level, but at the control semantics level. The engineering trade-off. This is where reality enters. Adding a user layer adds power, but also complexity. Now you must manage function block scheduling, execution timing, inter-device dependencies, deterministic behavior across vendors. This is why commissioning Foundation Fieldbus feels different. You're not wiring loops, you're orchestrating distributed execution. The architecture enables extraordinary flexibility, but demands architectural discipline. The mental model to lock in. Here's the clean way to remember it. OSI data moves. Foundation Fieldbus user layer, how control behaves. Without the user layer, devices can communicate with the user layer. Devices can cooperate. That distinction explains everything about Foundation Fieldbus, its promise, its power, and its complexity. And now that you understand where interoperability is enforced, the next question becomes inevitable. If control blocks execute across multiple devices, who keeps time and who decides when each block runs? That's where scheduling, link masters, and deterministic execution enter the picture, and where Foundation Fieldbus truly earns its reputation. Foundation Fieldbus H1, the physical layer that forces discipline. This episode is where Foundation Fieldbus stops being philosophical and becomes unforgivingly physical. because no matter how elegant the architecture, no matter how standardized the function blocks, everything collapses if the H1 physical layer is misunderstood. And H1 is not Ethernet. It does not behave like Ethernet. It does not forgive Ethernet thinking. Hash H1 at 31.25 kbps. Slow by design, not by accident. Let's start with the number that makes ITP people uncomfortable, 31.25 kbps. Yes, it's slow, deliberately. Foundation Fieldbus H1 was designed for process plants, long distances, hazardous areas, it determines execution, power, and data on the same pair. The tutorial is explicit here. The H1 physical layer operates at 31.25 kilobps SA and carries both communication signals and device power on a single twisted pair D to gain stability, noise immunity, predictable timing, intrinsic safety compatibility. In process control, certainty beats throughput. Shack, power plus communication on the same pair, the real constraint. This is the defining feature of H1. Unlike Ethernet or RS-485, H1 devices are bus powered. The same two wires carry DC power, AC communication signal. This creates a very different electrical reality. You are no longer designing just a data network. You are designing a distributed power system with communication riding on top. That's why current draw matters, voltage drop matters, spur length matters, device count matters. Ignore any of those and the bus becomes unstable, often intermittently, which is the worst kind of failure. Terminators, non-negotiable. Exactly, 2H1 is a transmission line. Transmission lines must be terminated correctly. Foundation Fieldbus requires exactly 2 terminators, one at each end of the main trunk. The tutorial states this clearly. Terminators are placed at each end of the pair to eliminate reflections, not 1 terminator, a terminator on every spur. Exactly 2. Why? Because reflections at 31.25 kbps distort signal edges, break synchronization, cause sporadic communication loss. Most H1 problems in the field trace back to missing terminators, extra terminators, terminators placed on spurs instead of the trunk. This is not tuning. This is physics. Trunk and spurs, why topology is strict. Foundation Fieldbus H1 uses a trunk and spur topology. The trunk is the main highway, spurs connect individual devices. The tutorial emphasizes that spur lengths are strictly defined and limited. Why the restriction? Because spurs bet transmission lines. They reflect signals, they add capacitance, they distort timing. Long spurs don't fail immediately. They fail under load, during commissioning, or when a new device is added. That's why H1 enforces discipline. Short spurs, controlled device count, defined topology. This is not flexibility, this is predictability. The 1900 meter rule, distance with conditions. One of the quiet strengths of H1 is distance. The tutorial specifies that the maximum trunk length can reach 1900 meters, provided proper power conditioning and termination are used. But that distance is not free. It assumes correct cable enditioners, controlled spur lengths, known device current draw. Exceed any one of those assumptions and the distance limit becomes theoretical. H1 gives you reach, but only if you respect its electrical model. Power conditioners, why you can't just inject 24 volts. Another subtle but critical point. The power supply feeding an H1 segment is not a raw 24 volt source. It must include a power conditioner so that DC power feeds devices. AC communication signals are not absorbed by the supply. The tutorial calls this out explicitly. Without power conditioning, the data signal would be drained into the low impedance power supply. This is a classic mistake. Open quote, it's just 24 volt, let's hook it up, close quote, dot, no conditioner. Hack the physical layer mental model. You must keep Foundation Fieldbus H1 is not a fast network, a flexible topology, a forgiving system. It is a power-limited, distance-optimized, deterministically scheduled, process-focused bus. Every rule exists because something broke badly before it was written. The one truth that explains all H1 rules. Here's the sentence that ties everything together. H1 is a powered distribution system pretending to be a network. Once you see it that way, terminators make sense, spur limits feel obvious, distance rules stop being arbitrary, commissioning becomes methodical life. And with that physical discipline understood, you're ready for the final missing piece. If multiple intelligent devices share this powered bus, who controls time and who decides when data moves? That's where link masters, LAS, and deterministic scheduling step in, and where Foundation Fieldbus truly separates itself from everything else. Foundation Fieldbus data link roles: who speaks, who schedules, who keeps time. This is the episode where Foundation Fieldbus fully shows its character. Up to now, we've talked about power and communication sharing a wire, function blocks executing in devices, control moving into the field. But none of that works unless time itself is controlled. Because once multiple intelligent devices share one bus, the most dangerous question is no longer open, quote, can they communicate, close quote. It becomes open quote, who decides when they communicate, close quote. That responsibility lives squarely in the data link layer of Foundation Fieldbus. Why FF needed more than simple access control. Classic networks solve access in two broad ways: contention, listen, collide, retry; token passing, take turns. Foundation Fieldbus chose neither, at least not in the traditional sense. Process control cannot tolerate random delays, retry storms, unbounded latency. So FF introduced something stricter: open quote, a scheduled conversation enforced by time authority, close quote. That authority is called the LS, Link Active Scheduler. The three data link roles: not all devices are equal. Foundation Fieldbus deliberately assigns roles to devices on the network. This is not optional. This is how determinism is achieved. The tutorial defines three device types at the data link layer: link master, bridge. Each exists for a reason. Basic device: I publish when asked. A basic device is typically a transmitter, a valve, a simple field instrument. Its defining characteristic is this: open quote, it cannot control the schedule, close quote. A basic device executes its function blocks, holds process data, responds when instructed, publishes data when compelled. It never decides when to speak. This is intentional. Basic devices are predictable, lightweight, focused on process interaction. They obey time. They do not create it. Link master: I can keep time if needed. A link master is a more capable device. Examples include controllers, advanced field devices, interfaces with higher intelligence. A link master understands the schedule, can become the LS, can issue control messages, can maintain network timing. But here's the subtle point. Open quote, a link master is eligible to be LS, not always the LS, close quote. This allows redundancy. If the active scheduler fails, another link master can take over. The bus doesn't collapse just because one device disappears. This is fault tolerance by role design. Bridge: I connect worlds. A bridge connects one Foundation Fieldbus segment to another segment or network. It doesn't just forward raw bits. It translates timing domains, maintains determinism across segments, preserves scheduling integrity. Without bridges, FF would be trapped in isolated islands. With bridges, FF becomes scalable without losing discipline. LAS, the quiet authority on the bus. Now let's talk about the heart of the system. The Link Active Scheduler LAS is not a device type. It is a role assumed by one link master at a time. The LAS is responsible for maintaining network time, enforcing the communication schedule, issuing compel data commands. Think of LAS as the straw. No musician decides when to play, the conductor does. Compel data: now is your turn. This is one of the most important phrases in Foundation Fieldbus. Compel data is a command issued by the LAS that tells a specific device, open quote, publish your data now, close quote. When a device receives compel data, it places its data on the bus, other devices listen, subscribers consume the data. No collisions, no guessing, no retries, just scheduled truth. Publisher, subscriber, not request, response. Notice how different this is from polling. In Foundation Fieldbus, a device publishes data, multiple devices can subscribe to it. Data is identified by content, not destination. The tutorial explains this clearly. Scheduled data transfer allows one device's data to be used by multiple subscriber devices. This is incredibly efficient. One TRAN role loops, displays, diagnostics, logs all at once. Scheduled versus unscheduled communication. Foundation Fieldbus separates traffic into two worlds: scheduled cyclic communication, process data, control loop variables, time-critical information; unscheduled acyclic communication, configuration, diagnostics, maintenance access. The last guarantees that scheduled traffic always gets its slot. Acyclic traffic fills the gaps, never the other way around. That ordering is why FF remains calm under load. Why this matters more than speed. Let me be very direct. Foundation Fieldbus does not win by being fast. It wins by being predictable. Every device knows when it will speak, when it must be silent, when data will arrive. That certainty is what allows control loops to execute in the field, multiple vendors to interoperate, power and communication to coexist, long segments to remain stable. The mental model to lock in. Here's the clean way to remember FF data link behavior. Basic devices hold data, link masters understand time, LS enforces order, compelled data replaces contention, publisher-subscriber replaces polling in the say. This is not networking borrowed from IT. This is time-governed communication built for process control. And once you truly understand this layer, you understand why Foundation Fieldbus can do something most networks cannot. Open quote, run control loops without ever asking permission from a controller. The SAS close quote, that's not magic, that's architecture. Function blocks, AI, AO, PID, ratio, control without a PLC. This is the episode where Foundation Fieldbus stops being a network and becomes a control system. Because once you truly understand function blocks, a quiet realization hits. Open quote, the PLC is no longer mandatory for control. Close quote. That sentence alone explains both the power and the controversy of Foundation Fieldbus. Why function blocks exist at all traditional automation follows a familiar hierarchy. Field devices measure and actuate, PLC DCS executes logic, HMI displays results. Field devices are informants, controllers are decision makers. Foundation Fieldbus intentionally breaks this hierarchy. It says, open quote, if a device already has a processor, memory, and timing, why can't it participate in control? Close quote. That question changed everything. Hashed function blocks, control as a standardized language. A function block is not just a chunk of code, it is a standardized behavioral object, defined by the Fieldbus specification, not by vendors. The tutorial lists typical blocks such as analog input, analog output, AO, PID, ratio find inputs, defined outputs, defined execution behavior, defined timing expectations. That definition is what enables interoperability. A PID block is not vendor A's PID. It is the PID block. Analog input AI, where reality enters the system. The AI block lives inside a field transmitter. Its role is to acquire the raw measurement, apply scaling, apply status and quality, publish a usable process value. This is critical. The AI block does not just send a number, it sends meaning, value plus quality plus status. That richer context is why diagnostics become possible at the control level. Analog output AO, where decisions become action. The AO block lives inside actuators such as control valves. It receives a command value, applies limits and modes, drives the final control element. The AO block does not blindly obey, it understands. Manual versus automatic, fail-safe behavior, status feedback. This makes the actuator an intelligent participant, not a dumb endpoint. Block, control logic moves into the field. This is where the real philosophical shift occurs. The PID block can live in a controller or inside a field device itself. When the PID block executes in the field, measurements arrive locally, output commands are issued locally, control loops close without leaving the segment. The tutorial explicitly highlights this idea by embedding function blocks at the field level. Foundation Fieldbus eliminates the need for a central PLC to perform control role. That reduces the central hardware, single points of failure. Control becomes physically closer to the process. Ratio and advanced blocks. Cooperative control blocks like ratio, arithmetic, and selector exist to support multivariable relationships, coordinated control, process logic at the field level. This allows devices share values, subscribe to each other, cooperate without a controller, orchestrating every step. Control becomes distributed, not centralized. Hash control without PLC, what that really means. Let's be precise here. Foundation Fieldbus does not say, open quote, PLCs are obsolete, close quote. It says, open quote, PLCs are no longer the only place control can live, close quote. That distinction matters. PLCs still excel at sequencing, interlocks, high-speed logic, complex state machines. Foundation Fieldbus excels at continuous control, process loops, distributed execution, resilient architectures. They are different tools for different layers of control. Scheduling, the invisible backbone of field-level control. Here's the part that ties everything together. Function blocks are scheduled, not free-running. Their execution depends on LAS timing, compelled data cycles, deterministic communication slots. If scheduling is wrong, loops destabilize, blocks execute out of sequence, control degrades silently. That's why episode 7.4 mattered. Function blocks only work because time is governed, communication is deterministic, execution order is guaranteed. Control without a PLC only works if time itself is controlled. The mental model to lock in foundation Fieldbus function blocks represent a fundamental shift. Control logic is portable, execution is distributed, devices are collaborators, the network is time-governed. Once you understand this, foundation Fieldbus stops being complex. It becomes clear, intentional, and in the right applications, incredibly elegant. And now that you've seen how control lives in the field, the final question naturally arises. What does this mean for design, maintenance, and failure modes in real plants? That's where theory meets operations, and where engineers either trust the architecture or fight it.